Hi, friends. First of all, thank you all for joining us here. I know it's a 5:40 p.m. session on day 3 of the conference, and drinks are being served outside, so it's a tough call for you. So my name is Adar Danait. I'm a principal engineer in digital cloud and technology team at Citi.
Hello, friends. I'm Lilian Ernest. I'm a lead engineer, also the digital cloud and technology team at Citi.
And today we are going to talk about fault tolerance as a requirement and not just a feature. So before we get started, let me ask you all a question. How many of you have been in a situation where you built a system, taken it live at scale, and realized that it needs a little bit of more hardening to make it fault tolerant and resilient? Right? So we've all been there. So we at Citi, we started on our path to transform our legacy monolithic applications to microservice architecture a couple of years ago. And that's when we realized that having a plain vanilla microservice setup is really not enough. So we need to apply some fine-grained fault tolerance controls and patterns to our services, in fact, to our code, in order to really make them fault tolerant and resilient and scale at large. So our key takeaway for today is going to be some of those patterns which we were able to apply to our services and which really helped us to scale them at large. So this is going to be our agenda for today. We are going to start off with defining our problem statement. Then we are going to get into some of the basic concepts and coming up with a solution to solve the problem. Then we are going to go into some of the advanced patterns and configurations which really worked well for us to solve the problem. And then we are going to wrap up with a demo which illustrates some of those patterns in action. Right? So let's get started. First thing first, what does a typical microservice setup look like? An ideal setup for a microservice architecture should have services which are built on 12-factor apps principle. They should be all interfaced via REST APIs. So like if you can see in this picture, my digital applications are interfacing my bounded context services via REST APIs. They should be self-sufficient services, which means they should take care of their own data. And they should be contained within a specific domain. But this is an ideal setup. We all know that reality is something different, right? So in reality, we have services which are dependent on 2 or more other services on an average. And to complicate things further, we have cross-domain referencing between services, which means, like in this case, my reward service is going to depend on my account service, and my offer service is going to depend on my account service as well. In order to give you a glimpse of this situation in production in real time, this is a service flow map of one of our digital application at Citi in production. And you can imagine the level of inter-service communication and dependency you can expect in real time. So in order to define our problem statement, let's try to lock down upon a use case, which we are going to leverage and elaborate in remainder of our discussion. So our use case here is a customer-facing web application, which provides the customers with all the eligible offers. So I have a web application in the mix. I have an offer service, which acts as an aggregator or an orchestrator service, which talks to 3 other dependent services, namely merchant offers, location offers, product offers. And each of those dependent services, they have a backend system to support for data. Now let's consider a positive scenario for my use case. I have a single user request coming in. All my backend systems, all my dependent services are performing good. They are well within the SLA. So I get a 200 OK from all the dependent services and backends. I'm able to give the offers back to my customer, and my customer is happy. Let's consider the same system under tremendous load. I have a 50 requests per second coming in. My backend systems are still doing good. I'm able to appropriately scale my services to satisfy the load. I should be able to give offers back to my customers, and I have a happy customer family. Now let's take a negative scenario for the same use case. I have a single user request coming in. All my backend dependencies are still doing good, except for the location offer service. If you see there is something unique about the location offer service, it depends on a third-party system to provide the data. And we all know that the stability and the reliability of third-party system is way beyond our control. So in this case, my third-party system has decided to laze around a bit. All the calls to my third-party system are timing out with error 408, which means my location offer service is also timing out with an error to my offer service. But my offer service for a single user request load still has some data to provide to my customer from merchant offers and product offers. So things are not too bad. So I should be able to provide offers to my customer, and my customer is still happy. But consider the same use case, same situation under a tremendous load. I have a 50 requests per second load coming in. What's going to happen is my offer service, all the resources and threads within my offer service are soon gonna be waiting for data to be coming back from location offer service. So that's gonna basically trickle and cascade the latency to my upstream systems, and this is gonna have a significant performance impact. My customers are gonna experience longer wait times and load times, and that's gonna make them really unhappy. So what is our problem statement here? So our problem statement is if you have a highly interdependent distributed microservice system, and you have a single component or a single dependency which is latent, that can have a significant performance impact on your entire application. So that's our problem statement which we have to solve for. So what do we need to fix this? Do we need timeouts for our dependencies? You definitely need timeouts, right? Timeouts are a must, but under load, your throughput is much lower than the demand you have on your system, so your timeouts are really not gonna help. Do we need more aggressive timeouts? Probably yes, definitely you need more aggressive timeouts if you're confident that your backend system SLAs are well defined. But based on our experience, we found out that aggressive timeouts are just gonna prolong or delay the cascading from happening at a later point in time. It's not gonna prevent it. So what we really need is a system or a mechanism which is fault tolerant, which is able to detect the failures well ahead of time, and once they detect it, the system should be able to fail safe and fail fast. And we need a retry mechanism, a robust retry mechanism, which should be able to detect that my failures are now recovered and rectified, and it should be able to regain the system back to normal. Now let's try to draw an analogy with this situation and a real life example. So here I have an uninterrupted electric supply line coming from the supply tower to my household, and I have large number of appliances connected to my power outlet. What's gonna happen if there is a sudden electric voltage surge in the supply line? All my appliances are gonna go for a toast, right? So how do I prevent this situation? What do I need to do here? Any guesses? So I need a component called circuit breaker in the mix, which should be able to detect a high voltage line coming in. And the moment it does that, it should be able to trip the circuit so my appliances are prevented from getting damaged. So now let's take this circuit breaker pattern from my household and let's apply it to our application, to our use case. So a circuit breaker pattern in our use case should be able to detect the large number of failures happening on my location offer service. And the moment it does that, it should be able to trip open the circuit so that there are no more calls being made to my latent dependency. And this is going to prevent the cascading from happening. And also it should have a retry mechanism. It should be an always alive system, so it should have a retry mechanism which should be able to detect that location offer service has now recovered or rectified its fault. And the moment it does that, it should be able to close the circuit again so that the system is regained back to normal. So a typical circuit breaker pattern in a software application consists of 3 states, as we saw. First is the closed state, which is a good state. Everything is flowing good. The second one is the open state. So basically, when the errors or the faults have gone above the threshold, the circuit should open up, which should prevent the failures from getting cascaded to upstream systems. And third one is a half-open state, which is basically the retry state, which should be able to detect that the failures have gone below the threshold. And if yes, it should be able to close the circuit, or if no, it should be able to keep it open. So these are some of the popular frameworks in the Java world which allow us to implement circuit breaker pattern in our application. But today, we are going to primarily talk about Hystrix. What is Hystrix? Hystrix is a fault tolerance resiliency library provided by Netflix open source. It's bundled as a part of Netflix open source software, and also provided as a part of Spring Cloud Starter Kit. What it allows us to do is it allows us to identify critical integration points within your application and protect those integration points behind a circuit breaker pattern. So let's see how do we set up Hystrix. So if you are using the opinionated Spring Boot framework to build your microservices, setting up Hystrix is a real easy 3-step process. Step 1 is to add a dependency to Spring Cloud Starter Hystrix in your application maven pom.xml. So in our use case, we'll add this dependency in our offer service because that's where we want to apply the circuit breaker pattern. Step 2 is to annotate the function you want to protect behind circuit breaker with @Hystrix command. And then if you can see, you can also supply an additional attribute to that annotation. So in this case, I have specified a fallback method to be executed when the circuit is open or whenever there is a fault or an error. And step 3 is basically to annotate the Spring Boot application class itself with @enable circuit breaker, which will basically do the trick for you. So now that we have enabled Hystrix in our use case, let's see how it really works in action. So on the right side, we have the protected get location offers function. On the left side, we have the Hystrix execute command. So let's consider a positive scenario. So basically, the Hystrix execute command acts as a proxy or a filter for any call which is being made to the protected function. So in the positive scenario, the request comes in for get location offers. First thing Hystrix command is going to do is it's going to check if the circuit is open. If it is open, if in this case it's not, so it's going to make a call to get location offers. My location offers is performing good, everything is good, I get a success back, so no failure, no timeout. It's going to return the success result back to the caller. Let's consider a case where my get location offer service is failing with an error or timing out. In this case, my Hystrix command is going to step in, and it's going to execute the fallback method instead and return the fallback results back to my caller, if in case you have specified the fallback in your annotation. And on top of it, it's going to have a continuous loop of circuit health check, which is going to check if my failures or my errors have gone above the threshold. And if yes, it's going to trip open the circuit so that the subsequent call that comes in is going to get tripped right there and directly go to the fallback without even making a call to the location offer service. So this is going to help us prevent the cascading from happening. And last but not the least, there's going to be a retry in periodic intervals, because remember, it's always a live system. So it's going to periodically check if the location offers has rectified its fault. And if it has, then it's going to basically close the circuit and regain the system back to normal. So now that we have looked at some of the basic concepts of circuit breaker and Hystrix, I'm going to trip this circuit and fall back to Lilian, who is going to talk about some of the advanced patterns and configuration in Hystrix, which really worked well for us in Citi.
Thank you, Adar. At Citi, we've been using Hystrix for a while now. And there are several patterns and practices that we have observed that have worked really well for us, and now we'd like to share them with you. The first one is the advanced circuit breaker that Adar just talked about. It's a very sophisticated mechanism that we can integrate with our code with just simple annotations and configurations, which gives a lot of power for very little code on our part. The second pattern is the configurable thread pool pattern, also referred to as the bulkhead pattern. The third one is the thread isolation pattern. And we'll go into this in a little more detail and also look at how we can apply these. But first, a deep dive into our use case. So we have a web application that serves offers, 3 different types of offers. And it makes a call to the offer service, which in turn makes a call to 3 different services: the merchant offer service, location offer service, and the product offer service. What exactly causes an application that's running smooth and running fine to go down and bring the entire application down when one system is failing? So much that even if it's a small failure and in perhaps insignificant service, it has a potential to bring the entire system down. So when everything is going fine, I mean, on day 1, usually everything works fine and no complaints from customers. But suddenly we see a problem in the location offer service. Either it's not responding or it's responding very slowly. We see that the thread in the offer service that made a call to the location offer service enters into this waiting state. And it does nothing but just waits. The next request that comes into the offer service does the same thing. It enters into this waiting state and just blocks there. Within a matter of seconds, if you have a high enough load, you'll see that all the threads in the offer service enter into this blocked or waiting state. And what happens next is, in a matter of seconds again, all the threads in the web app also have the same effect. They're all blocked. And to make matters worse, the web app can't receive any more requests. The requests start queuing up, and the users just get a loading icon that's spinning infinitely and makes for a very angry customer base. So here is why we need Hystrix, and we need that circuit breaker pattern to prevent this from happening. So let's assume we implement the Hystrix circuit breaker into this offer service. As you know, the Hystrix circuit breaker will detect any failures and will shut off calls to the service. So when that happens, we're able to now show and display the offers page to our customers, and they will be able to see the merchant offers and the products offers displayed just fine. Only they will not be able to see the location offer service. And the retry mechanism in the Hystrix will automatically detect that the service is back up and restore all calls back to normal. So coming to the implementation aspect of this, as we have seen in one of the previous slides, it's the Hystrix command annotation that does the trick. So let's assume we have a method called getLocationOffers, which has the implementation to call the to call the location_offers service. When we annotate that with the Hystrix command, that provides the full circuit breaker implementation, which takes the state from closed to open and then retries and moves it back to closed. And additionally, we have the option of providing a command key attribute, which allows us to provide further fine-grained controls through our properties file. The additional configurations are the request volume threshold, an error threshold percentage, which is basically a percentage that has to be met before the circuit will trip, and a sleep window in milliseconds, which is the time period that the circuit breaker will wait before it trips. It's worth mentioning here that Hystrix has very sensible default values for each of these configurations, so you don't really have to override them unless it's necessary. So the biggest advantage or benefit that we've seen is that we've been able to fail fast because the circuit breaker does an early detection. It knows that slow wait times are coming ahead, and it shuts off all calls and allows us to take an alternate route. We may choose to provide an error response back to our users, or we could even have a stubbed response back to our users. And the other benefit is it allows us to provide ample space and time for a failing system to recover instead of beating requests upon a system that's already failing. So we can improve the chances of that system to recover. So now that we have a circuit breaker mechanism in place, has our system become completely fault tolerant and resilient? What we've seen, it has not. There are still scenarios where we would still experience latency and threads would hang and take our application down. So consider this. Let's say the location_offers service is responding slowly, but it's just within that timeout setting that we've defined. So let's say we have a timeout setting defined at 500 milliseconds, and the location_offers service is responding at 400 milliseconds, which is still slow. So what will happen is every thread will wait for at least 400 milliseconds until it resumes execution. The circuit breaker will not detect this as an error because the timeout has not happened, but it's still going to cause our threads to pile up, accumulate, and cascade all the way down to our users. So what we really need is a way to limit the number of threads that can enter into a waiting state. And we can do this using Hystrix. So Hystrix provides a way to allocate and define a thread pool and basically assign X number of threads associated with that dependency, such that at any given time, only that many number of concurrent calls can be made to that dependency. So even if there is a problem, it's only those threads that we've already assigned to that thread pool that are affected. And when that thread pool has reached capacity, Hystrix will not allow any further requests to be added into that thread pool. In effect, our service is going to stop making calls to the location_offers, and it's going to resume normal execution, and users will not see location_offers on the page, but they'll be able to see the other offers load up just fine. So the implementation of the thread pool, again, is very simple. Using the same Hystrix command, we assign what is called a thread pool key, and we provide a thread pool configuration in the application properties file. The configurations are core size, maximum size, and max queue size. It's important to define a reasonable thread pool size to ensure your application works efficiently. And it takes a little bit of trial and error, but here's one formula that can help. It's assess what transactions per second you expect to see in a production environment, and assess what average response time you expect to see under peak load. Multiply this, and this should give you the thread pool size you need, but always add a buffer to account for occasional latencies and network spikes. So in a situation like this where a circuit breaker doesn't solve our problem, assigning a thread pool key helps us to isolate a problem to one area and not allow it to spread to other areas, thereby keeping the error rate low, also keeping the number of users that are actually impacted by this very small. Whoa. Okay. It also helps protect downstream services from being overloaded. So let's say a rogue client decides to suddenly overwhelm your service with a lot of requests that you're not prepared for. It helps protect downstream services from being overloaded in this scenario. And for us, it's enabled us to operate with an optimum number of instances. So we don't have to keep scaling our instances to account for occasional network spikes because we've taken control of the threads within our application. All right. So we have a circuit breaker mechanism in place. We've been able to assign dedicated thread pools for our dependencies. Have we been able to become totally resilient? We found out from our experience that there's still scope to improve. Consider this. A lot of times when we integrate with third parties, we tend to use third-party libraries as client libraries that perform that network call implementation for us. They are black boxes. We don't have much control over them, but we heavily rely on network timeout mechanisms and retry mechanisms that are provided as part of those libraries. And what we've seen is a lot of times those timeouts are either not implemented correctly or they break when we go from one version to another version. So timeouts don't happen when we expect them to. Threads can go into indefinite waiting states, and this can cause our application to go down. So we need a mechanism to protect ourselves against this. So Hystrix provides a way to introduce a new thread layer that will associate with dependencies and separate out from the threads that are processing requests. How it does this is when there's an incoming request and a thread begins processing that request, it offloads the work of calling that external dependency to a separate thread. And it sets a timeout of an expectation of how long it will wait for that thread to come back. So even if there is a slow response and latency, the calling thread does not have to be impacted. It's not blocked. It will time out, and it will continue and resume execution. So that way, we've been able to keep the request thread separate from the thread associated with that dependency. The way to implement this is by providing a setting called execution isolation thread, also associated with the same Hystrix command, and a timeout period in milliseconds. So how did this help? By allowing our request or enabling our request thread to walk away, we've been able to keep an always available pool of threads to serve incoming requests and prevent a scenario where all our threads are blocked. And also, we've been able to remove dependency on client libraries. So here are the basic Hystrix patterns that we wanted to share with you. We'd like to get into a demo and show a live application to illustrate this. So on my laptop here, I have an offers application. It calls 3 different services. It has a call to merchant offer service, location offer service, and product offer service. This is a Springboard application. I also have a web page here that's called My Offers. It has 3 sections for the different types of offers. This web page calls the offer service, which in turn calls the 3 different services. So as a first step, I have also opened this network console here to show how long the page takes to load. My first scenario is where everything is responding fine, there are no issues, and you can see here that the page has loaded in about 255 milliseconds, which is pretty fast. Now I'm going to introduce a latency in the location offer service. I'm going to make it respond in 5 seconds. All right. When I try to load the page now, you can see it's taking longer to load. And yeah, it took a little over 5 seconds. Now, under high volume, you can expect this performance to degrade even worse, and it probably get to a point where users cannot even see this page. So this is my offer service without any Hystrix implementation. Now I'm going to show how it's different when I have Hystrix implemented. So I'm going to start my next service, which is called Offers Service with Hystrix, which is the identical service, but has the Hystrix implementation integrated. Yeah. So here's my class location offers method that I have annotated with the Hystrix command. I have provided a command key called location offers Hystrix command and a thread pool key called location offers Hystrix thread pool key, and I've provided further properties in my properties file. Look, for the location offers command, I provided execution, isolation thread, and a timeout of 1 second. And for thread pool, I provided a thread pool size of 5. The service is started. I'm going to try and load the page again. Took about 3 seconds. Do that one more time. Yeah, took a little over 1 second. So what happened here is that the Hystrix timeout mechanism has kicked in. So since I set the timeout to be 1 second, the thread waited for 1 second and then timed out. If you notice, the circuit breaker has not tripped because it requires a certain error threshold to be met before the circuit will trip. So I'm going to illustrate that now by generating some load. I have a load client here that's going to send some calls to my Office service. Yeah. So with this load, my circuit breaker should have identified that the service is failing and the circuit breaker should have tripped. So when I try to load my page again, try that one more time. Okay. So the page loaded much faster now. It took only 300 milliseconds. Now it took only 86 milliseconds. So what happened now is the circuit has tripped and my application is not even attempting to call that failing service because it knows that it's already failing. So it's not even attempting. What I'm going to do next is remove the latency. And try to load the page again. Yeah, my page loaded just fine. It took a little over 100 milliseconds. All the offers are displaying fine on this page. This is because the circuit breaker has detected that location offer service is back in business, and it has done the whole retry mechanism and restored all calls to normal. That's Hystrix in action for you. Back to Adar.
Thank you, Lilian. So now that we have looked at the magic of Hystrix in action, let's try to quickly summarize the key takeaways for today. The first key takeaway mantra is fail fast and rapidly recover. So you should be able to detect the failures well ahead of time. You should be able to fail fast when you detect them and fail safe, and which will basically prevent the cascading from happening. And you should have a robust retry mechanism which should be able to regain the system back to normal. Degrade gracefully wherever possible. Try to leverage the fallback method provided by Hystrix in the annotation. It allows you to provide a subtle and meaningful response, error response back to your customers rather than just failing abruptly on them. Fault tolerance as a mandate requirement rather than a nice-to-have feature. So what has really helped us at Citi is to include things like performance, resiliency, fault tolerance as a part of our core user stories when we are building our features, and not just include them as non-functional requirements. What we have also done is we have deployed some quality gate controls in our CI/CD pipeline, which is going to basically ensure that all the recommended patterns and configurations are applied to a service, applied to the code, before the code is even delivered for system integration testing. And last but not the least, @Hystrix command is at your service, at your disposal. Identify the critical integration points in your applications and just annotate them with Hystrix command, and that will do the magic for you. With that, we conclude our session. Again, thanks for attending. You guys have a great evening and enjoy the rest of your conference. Thank you.